In the last video, we started talking about rational functions. Remember, a rational function is of the form p over q, where p and q are both polynomial functions. So it's a fraction with a polynomial on top and a polynomial on the bottom. And we discussed various places where these rational functions might not be defined. For example, if you had a vertical asymptote or if you had a hole. Today we're going to talk about some other qualities of a rational function that might help us eventually in trying to get a sense of what the graph of a rational function looks like. So we're going to start by talking about end behavior. Now remember, we had said that for a polynomial function, the end behavior always heads off towards positive or negative infinity, right? So it could look something like this, or maybe towards positive infinity or negative infinity. Not both, but some combination of two of these. And that's going to be true for rational functions as well. Your function could head off towards positive or negative infinity as x approaches positive or negative infinity. But with rational functions, we also have the possibility for a horizontal asymptote. Now, a horizontal asymptote is similar to a vertical asymptote in some ways, in that your function is approaching a particular value without quite reaching it. And so, for example, if you had a horizontal asymptote at b, that means that this is a weird looking dotted line here, this should be dotted. That means that your function, at least at its endpoints, are going to be eventually approaching that value as x heads towards negative or positive infinity. Now, it might cross that line, right? You might actually have an output of b at some point, but the asymptote really is just talking about what's happening towards the ends of your function as x heads towards positive or negative infinity, right? So it doesn't mean that it never reaches that value. It just means that that's what the output is as you're getting closer and closer, as x gets closer and closer towards infinity. Now, under what conditions is your rational function going to have a horizontal asymptote? Well, there's sort of three different possibilities here, and it has to do with the degree of the numerator compared to the degree of the denominator. Remember, the degree is just the largest exponent, right? So in the first case, suppose that the degree of the numerator is less than the degree of the denominator. So for example, if your function looked like f of x is x squared plus 1 over x cubed minus 2x, something like that. The rest of the stuff doesn't really matter, right? The rest of the polynomial doesn't matter. What matters is your leading term here. In particular, the degree of the numerator is 2 and the degree of the denominator is 3. So the other terms don't really matter. All we're comparing is the degree of the top to the degree of the bottom. Since the degree of the top is smaller than the degree of the bottom, this means that we end up with a horizontal asymptote at y equals 0. The reason for this is, as x heads towards positive or negative infinity, if you plugged in a really big number here, like a billion or a trillion or something very, very big, the number on top is going to be relatively small compared to the number on the bottom. A billion squared is big, but it's a lot smaller than a billion cubed. And so these other terms end up having sort of a very marginal effect on the overall numerator and denominator. And so because we have such a bigger number in the denominator, this fraction is going to essentially be getting close to 0. Right, so anytime the degree of the numerator is smaller than the degree of the denominator, you'll have a horizontal asymptote at 0. Now in the second case, what if the degree of the numerator and the degree of the denominator are the same? So let's say we had the function f of x is x squared plus 1 over x squared minus 2x. So it's similar to the last one, except now the denominator is x squared minus 2x instead of x cubed, so the degree of the top and the bottom are both 2. The largest exponent on both are 2. Well, in this case it says that you'll have a horizontal asymptote at y equals a sub n over b sub n. So a sub n over and b sub n here just mean the leading coefficients. In other words, the coefficient on the x squared term here. So our coefficient here is 1, our coefficient here is also 1. Right, if you don't see 1, you can assume that there's a 1 there, which means we're going to have a horizontal asymptote at y equals 1 over 1. In other words, just pull out that leading coefficient from the top over the bottom. 1 divided by 1 is just 1, so your horizontal asymptote will be at y equals 1. And now finally, for the third case, If the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. So let's say our function is x cubed plus 5 over 3x squared minus 7. The degree of the numerator is 3, and the degree of the denominator is 2, so we have a larger degree in the top than we do in the bottom. And this just means that we have no horizontal asymptote. That means you're in one of the cases that we saw in the polynomial end behaviors. It means your function is either going to be heading towards positive infinity or negative infinity on either side. Right? Not both of these, but one or the other, either heading towards positive infinity or negative infinity. All right, let's look at a couple of examples. Let's say we wanted to find the horizontal asymptotes for these three functions. 3x cubed minus 12 over negative 4x cubed plus 7x plus 8. Remember, what we need to do is compare the degree of the top to the degree of the bottom. They're equal in this case. They both have degree 3, which means we will have a horizontal asymptote. And we had said that whenever the degree of the top is equal to the degree of the bottom, to find the asymptote, you just pick out the leading coefficients. So my leading coefficient on top is 3, and on the bottom is negative 4. So I have a horizontal asymptote at 3 over negative 4. If I wanted to sketch this, I would need to put a point here at negative 3/4 on the y-axis, draw your horizontal asymptote, and the graph is going to have that horizontal asymptote down there at negative 3/4. All right, example B. We have 8x to the 5th minus 3x squared over 12x squared plus 7x minus 1. Remember, all that really matters here is that leading coefficients, right, the degree of the top and the bottom. On top, the degree is 5, and on the bottom, the degree is 2. So if the numerator has a larger degree than the denominator, then these outputs are going to be blowing up. They're going to be heading towards infinity. So there is no horizontal asymptote. And finally, in our last case, again, let's compare the degree of the numerator to the degree of the denominator. We've got a degree of 1 in the numerator, because 2x would be like 2x to the 1 power, and a degree of 2 in the denominator. So the degree of the denominator is bigger here. Degree of denominator is larger. And that means, whenever that happens, that we have a horizontal asymptote at 0. I should say at y equals 0. Okay, so this is going to help us in terms of trying to get a sense of what graphs look like. Now, we know where there might be vertical or horizontal asymptotes. We know how to find holes. One piece of information that we're missing would be different points on the graph, and so in particular, x and y-intercepts. Now, if we wanted to find the x and y-intercepts of a rational function, we're going to follow steps that are really similar to our steps for finding x and y-intercepts of polynomials. That is, normally to find an x-intercept, we set y equal to 0. In other words, we replace f of x with 0 and solve for x. But if your polynomial, or if your function is a rational function, right, it's a polynomial on the top and the bottom, and I set that equal to 0, the only time a fraction is equal to 0 is when the numerator is equal to 0. Right? That's the only possible way that that fraction could be equal to 0. And so what we're going to do is, to find the x-intercept, we're going to set the numerator equal to 0 and solve for x. Then you just want to make sure that whatever solution you get there is actually in the domain of the function, because if it's not in the domain of the function, it's certainly not going to be an x-intercept. To find the y-intercept, we're going to set x equal to 0 and solve for y. In other words, we're going to evaluate the function at 0. Right, replace x with 0, and see what you get for an output. That will be your y-intercept. So let's put all that together to try and get a sense of what a graph would look like. So we have this rational function x over x squared minus x minus 2. Now, I didn't say to find the domain, but it's useful to do that first, just so that you know later on whether something's an intercept or not. So the numerator is just plain x. The denominator I can factor as x minus 2 times x plus 1. Setting each one of those factors equals to 0 gives me x equals 2 and x equals negative 1. My function is going to be undefined here, because plugging in 2 or negative 1 will give me a 0 in the denominator. And so my domain is all real numbers except 2 and negative 1. Okay, so let's first try to find the x-intercepts and the y-intercept. So we had said on the last page that to find the x-intercept, we're going to set the numerator equal to 0. Actually, couldn't be simpler, right? Our numerator is just plain x. I don't even have to solve for x. By setting the numerator equal to 0, I'm already done. So I have an x-intercept at x equals 0. That's the origin. Now to find any y-intercept, I need to evaluate the function at 0. In other words, find f of 0. Well, what do you know? When you plug 0 into this function, you get 0 over negative 2, which is just plain 0. Okay, so the x-intercept and the y-intercept, in both cases, you get the point 0, 0. That's the only place your function is going to cross the x or the y-axis. Great. Let's move on to holes and vertical asymptotes. So remember, the only potential place for a hole or a vertical asymptote is anywhere your function is undefined. So that would be at x equals 2 or at x equals negative 1. We're going to plug each one into this function, try to evaluate this function at 2 and at negative 1, and see what the result is. Remember, we saw last time that if it's 0 over 0, it's probably a hole, and if it's a non-zero over 0, then it's a vertical asymptote. So plugging in 2 is going to give me, I'm just going to plug it into this factored version of my function up here. Plugging in 2 is going to give me a 2 on top and 0 times 3 on the bottom, so 0 on bottom. Non-zero over 0 means we have a vertical asymptote at that x value of 2. Alright, if I try to plug in negative 1 just like before, I'll have negative 1 over negative 3 times 0, which is 0. So again, non-zero over 0 means a vertical asymptote, this time at the x value of negative 1. Okay, so we don't have any holes. We have 2 vertical asymptotes, that's fine. And the last thing we want to know is, do we have any horizontal asymptotes? This is what we just talked about in this video. To find any horizontal asymptotes, we compare the degree of the numerator to the degree of the denominator. Well, the numerator has degree 1. It's just plain x, right? So we have degree 1 on top, and on bottom we have degree 2. It's a quadratic. And since the degree of the numerator is smaller than the degree of the denominator, this means we're going to have a horizontal asymptote, I'm just abbreviating that HA, at y equals 0. Anytime the degree of the denominator is bigger, your function is going to head towards y equals 0. So with all this information, I can try to get a sense of what this graph looks like. I've got a horizontal asymptote at 0 that's going to look like this. Then I've got vertical asymptotes at 2 and at negative 1. I'm not really labeling this well. This should be a 2 and a 1 here. The problem is this doesn't really tell me much. Okay, I also have this point at 0, 0. Remember, that's my intercept. So I know sort of the end behaviors, and I know that I have these vertical asymptotes, but what does the graph really look like? Right, so maybe it looks something like this if we try to fit it into these different asymptotes. It could look something like that. Right, it could always be positive, but it doesn't have to look like that. Maybe it looks something like this. I don't know. Right, there's a lot of different possibilities that you could fit a function into these 3 asymptotes. So I'm not actually going to ask you to graph these rational functions in this class. I want you to keep in mind the various different techniques that we've talked about, because when you get to calculus, you'll see exactly how to put these pieces together along with what you know in calculus to see just what exactly this function does look like.